Hello everyone, and in this video, we are going to cover the OSPF packet types, like how many different types of packets OSPF uses for its internal process. You can see like there are mainly 5 types of packets which are used by the OSPF for its internal process, right? Such as hello packet is there, then DBD, which is also known as database descriptor, and then link state request is there, link state update is there, and then finally there is a link state acknowledgement. So we have to cover each and every packet and its use case within the OSPF so that we understand the uses of all these 5 different types of packets within OSPF. So remember, as I said before, like in previous video as well, that OSPF does not use TCP or UDP, for transmitting its payload or its message. So OSPF uses IP protocol number 89, as we discussed in previous video. Therefore, it will directly interact with IP. However, there is the concept of OSPF header, right? Remember that OSPF header is going to be common for all these 5 different types of packets, or I would say messages, right? So, like, whether it's hello packet or DBD or LSR or LSTU, all these packets are going to have a common OSPF header. So first thing is first, let's get through that OSPF header first, right? So if we talk about the OSPF header, right? So that is the 24 bytes long common header for all different types of packets, like whether it's hello packet or DBD, as I said before, right? So this is how the OSPF header is going to be placed inside an IP packet. So you can see that there is a layer 2 header, which is of course kind of like Ethernet or maybe frame relay or could be anything. Then at layer 3, that would be like IPv4 header, and then we have OSPF header, and thereafter we have that OSPF packet, whether it is a hello packet or or DBD or LSR or U, right? But you must remember that this OSPF header size is 24 bytes. This 24 byte information is also known as like OSPF header, right? So every packet starts with this common 24 bytes. So these 24 bytes, these entire 24 bytes are going to be common for all packet types, right? So let me just explain it in more detail. Okay. So these 24 bytes, right, within the header, it starts from here and goes until authentication. So this entire 24 bytes are going to be common for all OSPF packets, whether the hello packet, like each packet will get started with these 24 bytes, these common 24 bytes, I would say. And these are fixed 24 bytes. So version indicates that which version of OSPF you are using, and this type field is really important. If it is type 1, which means it contains the hello packet. If this type field contains 2, which means further it contains like the DBD packet, right? So inside OSPF header itself, we have necessary information which can be utilized by OSPF to understand that which type of packet it receives from the neighbor. Like, for example, if a router receives a OSPF an IP packet, right? So by looking at the OSPF header itself, it can easily identify whether it is a hello packet or DBD or LSR, whatever, right? Because if it is type 1, which means it was a hello packet. If it is type 2, then it means that it was a DBD packet. And if it was type 3, that means that it will be a link state request. Type 4, link state update, and type 5 would indicate link state acknowledgement. As I said before, that we have in total 5 different types of packets, right, in OSPF, like hello packet, DBD, LSR, LSU, LSR. First 24 bytes are going to be common for all these different types of packets. So the type field this type field will be used by any device to identify that which type of OSPF packet it is, right? And then packet length and then route ID. So you must be aware with the router ID, right? That what router ID is in OSPF. Remember that in OSPF, router ID is something which is really important, because sometimes if router ID is like, let's say you have misconfigured the router ID, so it may hamper the OSPF neighborship as well in between two routers. So it is very important part of the OSPF processing, right? So router ID, if you don't know about the router ID, then I would say, like I would explain the router ID now, right? So router ID is represented in dotted decimal actually, right? Dotted decimal, like in the format of IPv4 address. However, it is not necessary that router ID should be allocated to any interface. Like it's not necessary to have that IP address allocated to any one of the interface. Like you can pick any IP address and you can use that as a router ID on your router inside the OS, right? But remember that it is always represented in dotted decimal format, right? And basically, I would say the format of IPv4 addressing. Even though if you are implementing OSPF for IPv6, the router ID still has to be assigned in the format of IPv4 only. So, and remember that ideally, like, I mean, from the technical standpoint, all routers must use unique router ID participating in a single area. Like in an area, if I have like 20 routers or maybe 10 routers participating in OSPF process, right, in OSPF domain, then we just have to make sure that all those 10 routers are using unique router ID. It should not mismatch, or like it should not configure the common router IDs onto multiple routers. If so, then there will be a problem related to the routing. And you can see even the route, if router ID is common on two routers, then they cannot really build the OSPF neighborship. Right? If there are two routers directly connected and you have allocated common router IDs on both of the routers, right? Then the neighborship will not come up between those two routers. And one more thing that you should remember, that if you do not allocate the router ID manually, then it can pick up the router ID automatically as well in OSPF particularly, right? So let's say you never allocated the router ID manually, then it will look for the highest loopback interface IP. Let's say if you ever created any loopback interface on your router, then it can pick an IP address from that loopback interface. If there is no loopback interface exists on your router, then it will look for the physical interfaces, and the physical interface having the highest IP address will be used as a router ID. Or you could simply assign it statically, and whatever you define statically will be used by the OSPF as a router. That has the highest preference when you configure it statically. Now remember, router ID is something which is not really needed to be routed in the network. Like it's not necessary that, okay, routes must be available in the routing table for the router IDs. No, that's completely different, right? Although if you are using loopback as a router ID, obviously routes will be there in routing table. But let's say you picked up some random router ID, and obviously then there will not be any entries in the routing table of the routers for those router IDs. Okay, so it's not necessary to have the router ID part of the routing table. Area ID is again part of your OSPF header itself, right? So again, it is a 32-bit long field, right? So that is why in previous video I mentioned that the range of the area ID is from 0 to 4.2 billion, just because of the 32 bits, right? Now in OSPF, like on Cisco routers, it gives you flexibility to specify your area ID directly in decimals, or maybe in dotted decimals in the format of IPv4 address as well. So that's up to you, that how do you want to define the area IDs while configuring OSPF on Cisco routers. Then checksum is there for security reasons, right? And then authentication type and then authentication is there, right? So the authentication is also part of the OSPF header, right? So in OSPF, if you are even sending the LSU, link state update, or maybe link state request to your neighbor, again, the authentication will be part of that packet. It's not like authentication will be part of only the hello packet. No, it's not. Because these 24 bytes are going to be common for all OSPF packet types, right? So that's why we call it, or we are calling it OSPF header. It's fixed 24 bytes long information that it carries. Okay, so we have had a discussion now about the OSPF header. Now let's have a discussion around the hello packet. So this is the hello packet. Okay? The hello packets are sent by the OSPF periodically in every 10 seconds in most cases, right? And the dead interval, of course, is 40 seconds. That means that if you do not receive any hello packets from your neighbor for 40 seconds, thereafter your neighbor will be declared as a dead, right? So that's the dead interval. However, like in case of NBMA, non-broadcast multi-access, your hello interval could be of 40 seconds and dead interval would be 120 seconds. So basically that depends upon the network type that you are using. As I had a quick introduction around the network types in previous session as well, in previous video, like where I defined, okay, in case of point-to-point or maybe broadcast, the hello interval is going to be 10 seconds and that would be 40 seconds. But in case of point-to-multipoint or maybe point-to-multipoint non-broadcast or maybe for non-broadcast type of network, then the hello interval is going to be 40 seconds and that interval would be 120. So that depends basically that which type of network you are using. And by going on to interfaces, you can always modify the network types as well, but that's not something that we are discussing here. So let's put that aside and let's focus back on the hello packet. So hello messages are sent by OSPF periodically in every 10 seconds, right? So remember that these hello packets are used by the OSPF for the neighbor discovery as well as, these hello packets will be acting as a keep alive, right? So for example, if you want to discover a neighbor, whether neighbor is, you have a neighbor on the wire or not, obviously hello packet will help you to identify or to discover the neighbor. But even if the neighborship came up, right, neighborship is up, absolutely fine, no problem. Still the hello packet will be sent by the OSPF periodically in every 10 seconds. And at that time, OSPF will be utilizing these hello packets as a keep alive, just to ensure that, hey, I'm still alive, right? So that OSPF will keep neighborship up and running in between the routers. Okay. Now remember that hello packets are always multicasted by default using multicast address 224.0.0.5, right? However, even I mentioned it before that OSPF can also send a unicast hello packet in case if you configured your neighbor statically. So if you defined your neighbor statically, then of course the hello packet can be unicasted, right? So now the hello packet contains all this information that you can see. The header is going to be common, like previously we saw this header information, right? So this header will be there. So your hello packet is going to start with this header, right? And then it will follow, it will be followed by all these fields like subnet mask of the interface, right? Let's say you enabled OSPF on one of the interface of the router, right? So immediately OSPF will start sending the hello packets out of that interface periodically in every 10 seconds. So it will keep the subnet mask value of that interface in its hello packet, right? And that is why in OSPF there is a condition that to bring the neighborship up and running between two routers, it is mandatory to match their subnet mask value. And that subnet mask value is part of your hello packet, right? Then hello interval is there. Like by default, it would be 10 seconds. However, in some cases, it can be 40 seconds as well. Options are there, right? Different options, those can be leveraged by the OSPF for some different reasons, right? And router priority is there. So, in most cases, router priority will be utilized by the OSPF for the election of DR, BDR, or maybe master and slave that we will discuss later on. That what are the DR, BDR. But all these things are carried by the hello packet inside the OSPF. Then that interval is there. DR router, like who is the DR, right? And then BDR router. And even it will contain the neighbor information. So for example, I discovered a neighbor, right? I discovered a neighbor. Give me a sec. Okay. So this is what I was telling, like even the neighbor information would be carried. So for example, if I discovered a neighbor, like there is a router 1 and router 1 had an interface like Ethernet 0x0, right? And over path Ethernet 0x0, and discovered a neighbor, right? So going forward, whenever that router will send any hello packet out of the interface 0x0, it is gonna keep that information in its hello packet, like who is my neighbor. I'll discuss this later. Like during OSPF neighbor states, I'm gonna explain the utilization of this neighbor field, but this is pretty important, right? So this whole information is carried by the hello packet. So remember that hello packets are used by OSPF for the neighbor discovery and to maintain neighborship. Like the hello packets will be acting as a keep alive as well. Then the next packet that we have is DBD, database description packets, and which are really important, right? So like, for example, if hello packets were exchanged between the routers and now routers agreed upon to build the neighborship by all the parameters were matching, and now they are looking forward to build the neighborship. So then thereafter, they will start sending the DBD to each other, right? So DBD is nothing but it describes the database, right? So for example, there are two routers, router 1 and router 2, right? And we enabled OSPF between them, okay? So router 1 will have its own database table. Router 2 will also have its own database, correct? So once they exchange the hello packets and they agreed to build a neighborship between them, then they will send DBD to each other. And basically the DBD is kind of like indexing of the book. Like for example, if I have a database table and I have so many different types of information in my database table, so I'm not going to carry that information inside DBD, but like kind of a summary information will be there in the DBD packet. It will not be a complete database, but technically DBD packets will carry the LSA header in nutshell, right? So DBDs are going to carry the LSA header. Like basically all of the routers, like in OSPF, there is a huge role of the LSS. Now probably you don't understand the LSS very well, but yeah, like LSA is pretty important. And later on, like once we are done with these packet types, then thereafter I'll go through the LSA types and all that in a separate video. So point is that in DBD messages, you are going to carry the LSA header, and LSA header will be used for it's going to contain only LSA header in itself, right? So basically, DBD will not carry the entire database, right? But it will carry the summary of the database, right? Those are basically LSA header. Now, you could ask a question that why only LSA header? So basically, OSPF is a linked state routing protocol, right? And OSPF exchanges a complete database between the routers. Like, for example, if there are two routers, router 1, router 2. So router 1 and router 2 will have the common database table. So if router 1 is having anything in its database table, it will have to provide to router 2. Similarly, router 2 will also have to provide its database information to router 1. However, there could be a situation where neighborship was already up, but suddenly it went down due to some link failure or some other reason. And then, it came back. So in OSPF, basically what happens if neighborship goes down, it will remove route from the routing table, but it will keep the LSAs in its database table, right? And next time when neighborship comes back up, right? So there is no need to exchange a whole lot of database tables, right? Because it will consume a lot of bandwidth, correct? So to minimize the utilization of the bandwidth, what it does, first they send DBD messages to each other, right? And DBD contains all the necessary information that routers can easily identify that which all LSS they need to exchange, the complete LSS, right? Like I have a lot of LSS in my database table, so I'll provide my LSA headers to my neighbor so that neighbor can look at its database table and can see that which all LSAs are missing. And if not, then there is no need to provide the updates again and again, right? So that will save some bandwidth, right? And of course, the convergence will be a little quicker, right? So that way, the DBD messages are playing very important role here in OSPF. One more thing that would happen by the help of DBD packets, and that is the master-slave election. So the master-slave election has to happen in between two routers, and that's mandatory. Like in case of DR-BDR, you might have heard that, okay, DR-BDR will be acted in case of the multi-access network, but that's not the case of master-slave election, right? So if two routers are building up the neighborship between each other, right? If two routers are building neighborship with each other, right, then master-slave election has to be done in between that, right? If routers are not building neighborship, fine, that's okay. Then there is no need to elect master or slave, right? But in case if the routers are building neighborship, right, then they have to elect master and slave, right? So initial DBD packets will be exchanged between routers, and initial DBD packet does not contain any LSA header, and those are mainly used by OSPF to elect master slave. Like initial DBDs will be used by OSPF for the election of master and slave, and we will see that later on, that why do we require master and slave in OSPF during the neighborship actually, right? Because I'll explain you that how does OSPF build the neighborship between two routers, and at that time I'll explain that what is the use case of master slave election. But remember that master slave election is also done by exchanging the DBD packets. DBD contain the master related information as well. So you can see that even this DBD packet is going to start with those common 24 bytes, and thereafter it will contain the interface MTU. And that is why we say that in OSPF the MTU needs to be matched, and then only neighborship can come up between two routers, right? Then you can also see that there are some flags like I and MS. So I is like initial DBD, M says like more DBDs, and MS is like master slave, right? So if this router is working as a master, right, then this MS bit will be 1, else it will be 0, right? And then DD sequence number is also there, which is again, plays a very important role. And then you have the LSA headers. As I said, like DBDs will contain only LSA headers, not the entire LSA, right? So this is DBD. There we have LSR, linked state request, right? So as I said, if DBDs have got exchanged between routers, right? So let's say I received the DBD from my neighbor, like one router received DBD from the neighbor. Then it will check its database table, which all LSAs are missing, which all information is missing, or which is outdated. So whether any information is outdated or anything missing, for that router will have to send the linked state request to its neighbor. Post receiving DBD, it is going to compare its database. And if it finds that something is outdated in the database table, or maybe something is missing in the database table, for that information, router will generate linked state request and will give it to its neighbor that, hey, I need this information, please give it to me. So again, for LSR, linked state request, right? Remember that it's not mandatory for a router to generate the linked state request if there was no modification in the database. Okay, that's one thing that you should always keep in mind. But in case if there was a modification, if there was a change, let's say I received the DBD and something is mismatching as per my database table, then router will have to generate the linked state request and will send it to its neighbor, right? Again, the LSR is going to start with those common 24 bytes, right? That's OSPF header, right? And thereafter, this whole information will be there inside the linked state request. You can see LS type is there, then linked state ID is there, then advertising router is there, and it may have like multiple fields, and that's why you have like continuity, like ... like LS type again, because I might ask for multiple LSs to my neighbor to share with me, right? So like, for example, multiple LSs were missing as per the DBD received from the neighbor, right? Then I'll have to request for each and every LSA whatever was missing in my database table, right? And that is why you may have multiple entries inside the LSR linked state request. Then linked state update is very important and one of the critical packets, right? Because this is something which carries the actual database. Right? Now remember, linked state updates will be sent by the router only if it receives the linked state request. If I do not receive any linked state request, I'm not going to send the linked state update message. However, if I receive the linked state request, then I must provide the linked state update to my neighbor, right? That's mandatory. And the linked state update actually carries the LSA, the complete LSA, not LSA header, because DBD carried only LSA header. But this time, linked state updates will carry the entire LSA. Now, what are the LSAs? That is something that we'll discuss later on. But remember that link state update is very important packet, and it basically carries your links information or your routes information. Just for your understanding purposes, I'll make that statement, right? So it is carrying the route information in itself, right? So LSUs will have to be sent by the OSPF upon receiving the link state request. That's mandatory. And remember that link state update messages are not periodic, because link state update messages are sent only and only in response to the link state request. However, there is a database refresh interval, right, which is predefined in OSPF, and that is by default 30 minutes, right? So there is a default database refresh interval that we have in OSPF, that is of 30 minutes. Like in every 30 minutes, routers will refresh their database table, right? So that's the case. Okay. So the LSU link state update will also be shared in every 30 minutes periodically, but that's something different that I'll explain during the lab itself, right? It is just used by, although we can stop it in OSPF, but again, like it's used by OSPF just to ensure that all routers are maintaining the latest information in their database table, or they are maintaining the latest data, just to ensure that there is a database refresh interval which is by default set at 30 minutes. So that's the thing. So link state updates are very critical, right? And will contain the LSA. And again, the header is going to be common for link state updaters. Then we have the link state acknowledgement. Link state LS. Remember, when a router receives the link state update, right? Whenever a router receives the link state update messages, because link state update messages are very critical and very important for OSPF. Therefore, OSPF will always send an acknowledgement back to the sender that, hey, you sent me link state update and I got it. I received it, right? So for that purpose, we have this LS link state acknowledgement, right? And this link state acknowledgement, mainly it carries the LSA header which was received from the neighbor inside the link state update message. Like inside link state update messages, I received maybe a couple of LSAs. So I'm going to include those header in the link state acknowledgement and will give it back to the sender that, hey, I received the link state update. That's it. That's an acknowledgement. And we have an external acknowledgement here in OSPF because we are not using TCP. Just imagine if we were using TCP in OSPF, then we would have never required this external acknowledgement. But since we are not using TCP, therefore we just have to we just have to acknowledge our neighbor that, hey, we have received the update messages, those were sent by you, right? So for that purpose, we have this link state acknowledgement. So that's all about the OSPF packet type. I hope you enjoyed the lecture. Thanks for watching.